time I left you with a big mess and prediction. So we have some symmetry estimates for the X mass and the cosmological constant. In the standard model, we have something like this. And in the standard model plus gravity, we have something like this. On the other hand, we did an explicit calculation for the X mass, and we found no problem at all. And well, even if we add gravity, we're going to be in the same situation. So we're going to have some calculable function of the observed X mass and Planck scale, but we're still going to have some parameter entering our calculation that we cannot measure. We can only fix it by measuring the X mass itself. And well, we kind of finished the last lecture on this cliffhanger. So on the one hand, you might think that the standard model is telling you that you shouldn't take this estimate seriously. On the other hand, I mean, this estimate is reproducing precisely what you get from the calculation. So and besides, just from a narrative point of view, if I spend so much time to derive it, you know that it must tell us something important. And in the end, the answer is the most obvious one. What this is telling us is not something about the standard model, but about what comes beyond. So if you extend the standard model, you have to somehow avoid that the calculation in the theory that extends the standard model gives you something like this, which is in great tension with experiment. So essentially, the X mass and the cosmological constant are a low energy observation of our element operator, which is telling you something about much higher energies than those that are associated with the mass and the cosmological constant. So you're measuring them to be some small value at low energy, but theory is telling you that they contain information also about much higher energies. However, well, you might think that the theory just keeps looking like the standard model forever. However, we've encountered similar puzzles in quantum field theory before. I alluded to one in classical electrodynamics at the beginning of the lecture, which now I'm going to make more precise. But we also found similar situations in quantum field theory. So exactly the same issue. So you make an estimate based on symmetry and dimensional analysis, and you find something which is orders of magnitude bigger than experiment. Then you actually compute the parameter in your low energy effective theory, and you find that it's a parameter that can only be measured. However, by the calculation or the estimate, you can associate a scale where you expect something new to happen to modify the calculation and avoid the tension given by the estimate. And the scale is roughly when the calculable part is roughly comparable to what you measured. So in the case of the X mass, you would expect something new to happen at a scale roughly given by this formula. And you might think that this is naive because, again, in the standard model, there is no real problem. You're just measuring it. And maybe at this scale, nothing is happening. But every time we encountered a situation like this before, something was always happening actually at a scale smaller than the one that you can predict from your low energy calculation. So here you can predict it from your low energy calculation because, as we've seen last time, you get something like this. And say if you were to replace the top quark with something new at a much larger mass, you would get something like this. So either from the actual calculation or from the estimate, you expect a new scale of roughly this order, which numerically, in the case of the X mass, is about a TeV. And so what we're going to do in the next 10 minutes is I'm going to tell you of 3 examples where this very simple intuition that something has to happen at this scale is actually realized in nature. And then we're going to see how to possibly extend the standard model in a safe way, so in a way that does not create any tension with the measured value of the X mass or the cosmological constant. And this kind of fits nicely in our discussion of last time, because the extensions of the standard model that are safe, that I'm going to show you, are also extensions where the X mass is calculable. So we're going to be able to turn this tension between an estimate and a calculation that tells us that everything is okay into an actual problem. So we're going to be able to compute the X mass in these theories and essentially turn this parameter into a measured parameter, and then see that if the scales in this new theory are too large compared to what we measure on the left-hand side, on the right-hand side, you must have a fine cancellation between parameters that have nothing to do with each other. So in one go, essentially, we're going to state what's the actual hierarchy problem, not this one, but where you can when we compute every single item on the right-hand side, and also possible solutions. Because these theories where the X mass is calculable are all theories where there is a new symmetry that essentially tells you that the calculation is saturated at a given scale. The reason why you cannot compute it here is because the X mass in the standard model remains sensitive to arbitrarily high energies. You don't know where the calculation ends, and you have to parameterize your ignorance by adding this low energy parameter that you can only measure. Instead, in these new theories, there is a symmetry under which the X mass transforms non-trivially. And so here you cannot just put any scale in your theory, but only scales that transform under this symmetry in the same way as the X mass. All right, so this is roughly the very abstract plan of the lecture today. Now let's get into it. So as we said, we're going to start with some history. So cases where this intuition that something must happen at a new scale is actually realized. And then we're going to do theories where the X mass is calculable, which essentially for today are going to be supersymmetry and scale invariant theories. And this gives us both a precise statement of the problem and a possible solution, at least for the X mass. For the cosmological constant, you will see that it's not going to work out just because of the scales involved, because the cosmological constant is already so much smaller than all particle physics scales that we've already probed. Before doing that, there's going to be, I'm just going to make a small addendum to the last lecture. So a precision on the calculation and an alternative way to discuss this estimate. So we're going to actually start by this small addition to what we already said. So concerning the calculation, it's really a lightening precision. So last time, if you remember, when we computed the contribution of the top quark to the X mass, we wrote this complicated function of m top, y top, and other parameters. I never put a nut on them. The reason is that at the level of our one-loop calculation, the Lagrangian parameters for the top and the measured ones coincide. So I was not cheating when I told you that you can compute this in terms of observables. You can convince yourself by essentially doing the same exercise that we did for the W mass. The one loop correction that relates the measured ones to the Lagrangian ones gives a two loop contribution to the X mass that we don't want to take into account at this order. Okay, so this is all I wanted to add to the calculation. What I wanted to add to the estimate is not so crucial, but there is a cute way of doing it in a different way, which is more similar to the EFT construction we had at the beginning of the lecture. So there is a way to state the exact same thing that we're stating here, which is the following. So imagine that, okay, you know the standard model at the weak scale, so at 100 GeV. Let me call this scale lambda infrared. And then imagine that you know that the standard model is valid all the way to some much larger scale that I'm going to call lambda UV. In the middle, well, you have only logarithmic running of the standard model couplings, so that become weaker and weaker, especially lambda QC, sorry, alpha strong, which is the bigger one. And so you can roughly imagine, I mean, you can roughly think of very zeroth order of the standard model as some sort of free conformal field theory. And so, well, at this scale lambda UV, you just want to write down all the operators compatible with the symmetries of the standard model with their coefficients given to you by dimensional analysis, exactly as we did last time. So, for example, you're going to generate objects like this. So all operators of dimension delta a priori are going to have some coefficient of order lambda UV to the 4 minus delta times some order 1 number. And so what is the low energy scale from the point of view of the UV theory? The low energy scale is just whatever you have in front of the operator. So this operator is still going to exist at low energy. And so you expect all dimensional full scales that you see at low energy to obey roughly this, this relation. And so you see immediately that if at high energies you have only marginal operators, for example, so where 4 minus delta is small, then it's natural to expect a big hierarchy. So you're going to have that even if C is order 1, provided it's a tiny bit smaller than 1, if you send epsilon to 0, you expect this hierarchy to be big. There's nothing wrong with that. And actually, as I will show you later today, this is precisely why we don't worry about lambda QCD. So we're making all this fuss about the X mass and the cosmological constant, but in the standard model there is another dimension full scale. It is dynamical, but it's there. It's lambda QCD, and the reason why we don't worry about it, it's precisely this one. It's because it's generated by marginal operators, and we're going to see it later today. However, well, let's say that you have something like the X mass. Okay, the X mass in the standard model is associated to a dimension 2 operator, as we've seen last time. So this is my O to the delta, and delta is equal to 2. And then here I would have that my IR scale over my UV scale is just a square root of this order 1 number. So if you really want to get out of your high energy theory a much smaller low energy scale, you have to explain why this number is so much smaller than 1. And okay, it might appear like I did something new, but if you think about it for a few minutes, it's easy to see that this is exactly the same as these estimates that we were doing last time. All right. So that concludes my extras, let's say. Now let me tell you why this intuition as worked out before. So in the case of the electron, we've already seen it, but let me show you more explicitly. So if you compute the mass of the electron in classical electrodynamics, you're going to have some contribution from whatever you put in the Lagrangian, and some other contribution from the electric field around the electron. And so imagine that you have probed electrons up to some scale of order 1/TV. Okay, so now I'm cheating a little bit to make the example more explicit. So let's say you went to LAP or to the LHC, you collided particles, and you found that the electron is an elementary particle, so it's point-like all the way down to a TV. At the same time, you also measure the electron mass, which is much smaller. And so you're kind of in the same situation that we are for the X or the cosmological constant. You have this contribution here to the mass that you can compute, and naively, it's much bigger than what you measure for the mass. And so the only way in which you can make sense of what you're finding is that this contribution is finally canceling against this other one, which a priori has nothing to do with it. One comes from the energy stored in the electric field, the other one is a Lagrangian parameter of an unknown UV origin. So the problem is exactly the same as what we were seeing before. If you do the calculation in classical electrodynamics, you find no problem because you have a free parameter that you have to fix by measuring the mass itself. If you do an estimate based on what you can compute, you find this tension. So exactly the same issue. And well, you can see that by looking just at the part that you can calculate, you can estimate a scale where you expect something to happen if you don't want any tension at all. And this scale is precisely 1 over whatever you measure for the electron mass. So 1 over alpha MEV. And as we were saying last time, this is exactly the scale where something dramatic happens. So you start having enough energy for a photon to split into an electron-positron pair. So you're going to learn that positrons exist. You're going to learn that classical electrodynamics doesn't work anymore. You have to replace it with quantum mechanics and quantum field theory. And then you're also going to learn that this calculation is wrong. And if you do the calculation in quantum field theory, you're going to find a very different result. And the new result tells you that even if the electron stays point-like all the way to the Planck scale, this gives a correction to the mass of order 10%. So you have no problem at all with an electron staying elementary all the way up to the Planck scale. So this is one very successful post-diction of naturalness. And we did not figure out that the electrons and positrons existed in this way, but we could have. However, you might argue that this is not quantum field theory yet, and that's also only one example. Maybe I've been lucky. But well, we know of at least 2 other examples in quantum field theory. We know probably more, but I'm just going to give you the 2 that are the closest to the actual problem we have. And in one of these 2 cases, we even used this fact to predict the existence of a new particle that was actually there. So the 2 examples are the pion mass difference, so the mass difference between a charged and a neutral pion, and the kaon mass difference. So as you probably know, as you keep going down in energy, the strong coupling, the coupling associated with strong interactions becomes larger and larger. At some point, it becomes so large that the perturbative degrees of freedom of the standard model Lagrange do not describe nature conveniently anymore. So you could still use them if you were able to compute non-perturbatively at infinite order, but since you're not, you end up writing down an effective description of your theory that has different degrees of freedom. So roughly, let's say, if you start with the standard model in the form that we wrote down on the blackboard last time at around the weak scale, so at the W mass, and you go down, at some point you encounter at scale, which is about 100 MeV, where your description of the strong sector becomes impractical. So you cannot use it to make predictions anymore. And down here, the degrees of freedom change. So you're going to trade quarks and gluons for pions and baryons and other particles. And you can very roughly think of these pions that we're going to talk about today and these kaons as bound states of two quarks. For the case of the pions, it's not going to matter. For the case of the kaon, you can think about it as a bound state of two down quarks, a down and a strange. So we didn't really go into the details last time, but in the standard model, there are three families of quarks and leptons. So there are three quarks of type up and three quarks of type down that differ by their electric charge. And also by their interactions with W and Z bosons. But okay, this is not going to be very important for us. I'm telling you just in case you have no idea what pions and kaons are, but it's not going to be crucial in our examples. For our purposes, pions and kaons are just scalars that exist below this scale. And there are two pions. Well, there's a charged one and a neutral one. And since the charged one interacts with electromagnetism, we expect some mass difference between the two. So they are in a similar symmetry multiplet, but electromagnetic interactions break this symmetry. For the reason that the photon is going to interact with the charged pion, but not with the neutral one. So there's going to be a contribution to their mass difference proportional to diagrams like this one. And as I told you, these are not fundamental degrees of freedom. So, and also they arise from a strongly coupled theory. So it's not so easy to compute their interaction starting from the standard model. In principle, this is just a low energy theory. We could integrate out high energy degrees of freedom and write it down, as we were trying to do last time. But the strong coupling poses some obstructions. So you have two options. You can either measure their properties at low energy, or you can do dimensional analysis, as we did last time. And well, in this case, dimensional analysis is enough. So this theory has a single scale that I call lambda QCD. And as we know, the potential or the Lagrangian has dimension of a mass squared times a Webb squared. So, or if you prefer, a mass to the fourth over a coupling squared. And so let me say that lambda QCD in my definition has dimensions of a mass. Then I'm going to define another scale which has dimensions of a Webb as lambda QCD divided by some coupling, which experimentally we know to be of the order of 4 pi. And so with these two scales, I know that every contribution in the QCD Lagrangian has to be of this order. And now I want to know how the vertex between a charged pion and a photon looks like. So we're going to have an electromagnetic gauge coupling times a photon. And to restore dimension, this is a coupling times a field. And so I have to put a mass scale because it's a coupling times a Webb. And then purely from Lorentz, we know that this is going to look like something like this. And again, from dimensional analysis, I can just put two Webbs for the two pions and 1 mass for the derivative. And so in the end, well, of course, this is as we are doing purely dimensional analysis, so there is an unspecified order 1 number in front. And in the end, well, I mean, we get something very simple. We didn't really need to do all this work. But I wanted to show you how people estimate terms in the chiral Lagrangian when they have no idea what they look like. It's really literally as simple as that. And the reason that it's so simple is that QCD has a single scale. So the only things you can put up here are lambda QCD and pion, and the only things that you can put down here are still lambda QCD and f pion. Okay, so with this vertex, we can estimate the contribution of this loop diagram to the masses of to the mass difference, and we're going to have some E squared times our loop integral. So we're going to have a momentum squared coming from the two derivatives in the two vertices. So I'm being rough because we just want an estimate. Then we're going to have a k squared from the photon propagator and a k squared minus m pion squared from the pion propagator, where you can take this m pion squared to be the average of the two if you want, or just be more precise and put the charge pion mass here. In any case, I mean, at this loop order, it's the same thing because the mass difference comes at order 1 loop, and so here you can even put the 3-level mass, and that's it. Okay, so now from you see by I that you have 4 powers of momentum in the numerator, 2 in the denominator, so naively you expect something sensitive to high energies like we found for the X mass. And so we can estimate this integral by cutting it off at the scale where we expect something new to happen, just like before. So now we have a factor of E squared times a loop factor, so we have an alpha electromagnetic over 4 pi, where I'm defining as usual alpha as E squared over 4 pi, times some large mass scale squared. Okay, again, I'm using dimensional analysis to estimate the integral, and I'm using this intuition that something new must happen when this calculable part equals the measured part on the left-hand side. And so now we can go ahead and measure the mass difference and alpha, and we're going to find that the scale where we expect something new to happen is roughly 850 MeV. And indeed, at just below the scale, so at 770 MeV, you find a new vector meson that is called rho that couples to pions in a similar way, okay, with a slightly different coupling in front. We call it G star, and changes this calculation, cutting off the sensitivity to high scales. So indeed, our very naive intuition that something new must happen at this scale is realized, and it's realized before you find any tension, unlike the X mass or the cosmological constant. And again, well, this was a post-diction. Okay, I mean, QCD at the time when we measured these things was a total mess. We saw all these particles more or less together, and we figured out this neat example a posteriori. So it's not that we predicted the rho meson with this kind of considerations, but it's certainly at the theory level an example where the intuition that these estimates based on dimensional analysis that we're doing are signaling something new at a given scale is actually realized in nature. Perhaps a more significant example is that of kaons, which is almost exactly the same. The difference is purely historical, which is that in the case of kaons, we did use this fact to predict a particle that existed. So as I was saying before, kaons are a mixture of 2 different kinds of down quarks. And if you remember, last time, very, very briefly, we said that when you diagonalize Yukawa couplings, again, we are living at the weak scale in the perturbative standard model, you have some coupling to the W boson, which mixes different families. In practice, let me imagine that you've observed only the lightest quarks, the three lightest quarks, which are up, down, and strange. Then the Lagrangian, you would see something like this. Where this theta c and is just an order one number, it's an angle, which is precisely telling you what we were saying last time, that the eigenstates of the mass matrix are not the eigenstates of weak interaction, so there is some mixing. Okay, so now you know that this exists in the standard model, and you know that at low energy you have these particles. So you have a k0, which conventionally, let me call it down times s bar, and then a k bar 0, which conventionally, let me call it d bar s. So from these high energy interactions, I know that at low energy these two guys are going to mix, because at high energy I can write a diagram like this, say ds bar, two W bosons, two up quarks, and they turn them into D bar S. So I can start with a K0 and end up with a K bar 0. Of course, I'm not sure at all that this is the correct convention. I don't remember what people use, but the two are equivalent. So I know that at low energy, I'm going to find some non-trivial mass matrix. So the K bar 0 and the K0 are going to mix. So I'm going to have something that looks like this. And I can compute this delta M from this interaction. So integrating out the W and matching onto the effective Lagrangian that describe these kaons. The central value of the mass, instead, I cannot compute it at all. I mean, it's a very non-perturbative effect coming from the quarks that make up this meson interacting with each other and with gluons, but I can still measure it. In any case, we don't really care about the central value of the mass, because the whole point of this story is that once you diagonalize this mass matrix, you're going to have two mass eigenstates that people call k long and k short, because they have very different lifetimes. And if you compute the mass difference between the two, as I told you, you can do it from these diagrams, and you're going to get something like this. So again, these diagrams have some high energy sensitivity, and I'm cutting them off at the scale where I expect something new to happen. This Fk is a non-perturbative object that, again, I'm forced to measure or compute on the lattice, is about 100 MeV. Essentially, it's telling you how much, let's say, the perturbative quark bilinear overlaps with the meson wave function. And so, again, we can do what we've done so far and ask what's this new scale expected to be given the parameters that we measure on this side of the equation and on this other side of the equation. And we expect mu to be 2 GeV. And indeed, this was used to predict the existence of the charm quark, which has mass about 1 GeV. And what the charm quark is doing is essentially just coupling, just completing the orthogonal matrix here. So it's, here I should have written U bar. And when you include also these contributions in these diagrams, the high energy sensitive part is canceling out because you rebuilt an orthogonal matrix here.
Sorry, can you repeat this MU? I'll give you one.
Repeat what? MU.
MU that you gave me.
Yes. So, if I were to do a honest calculation, you would find something similar to what we found for the X mass. So you would find something that's sensitive to high energies and depends on a parameter that you cannot measure, measure independently of the mass difference itself, which is sensitive to high energies. Okay, but actually, let me not be precise in this case. So in practice, how I get this mu is I write down this integral, this loop integral, as we did for the pions. And I'm gonna find so I'm gonna find something like this. Okay. Now so I've cheated. So I've told you that I already know this Lagrangian, which when they predicted this particle, they didn't. So in reality, the only thing that they could compute was the low energy limit of this, which is this. So essentially, we're at momenta so much smaller than the W mass that you didn't know that the W existed as a propagating degree of freedom. So you are shrinking these propagators to a point. And so now you see again that you have an integral that diverges quadratically if you really want to go to infinity. So all I'm doing is that I'm regulating this integral with a hard momentum cutoff. And I'm putting it here. Okay. What's important? What's very important, even if now I'm being sloppy, is to keep in mind the lesson from last time. Okay. So I'm not saying that these issues come from divergences. Okay, so I'm just telling you that if you do the calculation, so this is mechanically the simplest way to estimate this mu. Okay. If you do the calculation honestly, as we did for the X mass last time, you would find a similar situation. So you would find something like let me call it delta m kappa 0 squared, kappa 0 squared. So you would find some parameter that you cannot measure plus some contribution that you can calculate. And then you're going to ask, when does this contribution become bigger than what I measured? And that's how you get mu. Okay, so this concludes the history lesson. I hope I haven't taken too long, because it was supposed just to be a curiosity.
I guess the reason they didn't do that for the top was because you can't make mesons out of it.
Because I didn't do it for the top.
Well, no, just you said this is sort of the one case where they actually predicted it, right? So I guess the bottom and the top were infeasible with the top because you don't get the mesons.
Let's see. So you would have to, so in this case, it was just because the charm was enough to cancel the divergence. There are cases where it's not, and you need to build the whole unitary matrix. But indeed, you would never know it at low energy, because this is a theory where the top has been long integrated out and also the bottom. But you can envision a similar example at higher energy, like you can say, I don't know, BB bar mixing. Then you would have the same, but then historically, I think they measure precisely BB bar mixing not so long. I don't remember if before or after the talk, but I mean, it was not an issue anymore. Sorry?
Yeah, but maybe for the coffee break.
Okay.
No, I was thinking that in the case of delta mk, the issue is not just that you need to, let's say, to regulate your multiple, but also to get, once you do things properly, as you were saying, to get delta mk right. And for that, you need the contribution of the charm to get it match the experimental value. But maybe that's not.
Yeah, I mean, yes, once you put the charm in, it becomes calculable. And then if you don't, well, the fact is that I don't know how to remove the charm and still leave it calculable. So, but indeed, I mean, once you make it calculable, then you know that the charm is there and it has the right mass. Then, yeah, I mean, in some sense, maybe the right way to answer is this estimate is telling you that the charm exists. Yeah. And then you can even predict the charm mass if you want to know, not just this upper bound, but you can precisely say, okay, the charm mass should be 1 GeV plus or minus.
To get agreement with.
Yeah, absolutely. Okay, so now let's get to the meat of the lecture. Maybe. It took a very long time, but maybe, well, let me ask you if, how do you feel by now about the whole story? Because I have a sense that being very precise about the problem might also make you feel like it's less of a problem. So that's why I give you this history lecture. So, but well, I don't know exactly what to ask you, but if you have questions about what we talked about until now, about the problem, its formulation, whether you feel that there is no problem, now it's the time to ask. You already asked to some extent, but if not, I'll just move forward and tell you about theories where there is an actual problem and also an actual solution. Okay. If no one is bothered by what we said so far, let me jump into supersymmetry. So I'm just going to write down the simplest algebra, so the one for n equal 1, which is enough for our purposes to understand what I mean by making the X mass calculable and finding a problem. So supersymmetry extends, so it's gonna, the algebra of supersymmetry is the usual algebra of Poincare, which I'm not gonna write down, plus the addition of two spin 1/2 generators. We have the following anti-commutation relation plus they, of course, anti-commute with themselves. Here. And they commute with momentum. And they have some more complicated relation with boosts and rotations. So I bother to write the algebra because it's really all we need to understand what's going on in theories like this one. So as we said, our estimates are telling us that the standard model cannot be extended trivially if we want to make sense of the cosmological constant and the X mass. And this is one possible extension that could make sense of them. And the reason is purely within the algebra. So I was not planning to talk about the cosmological constant today, but let's see. Okay, let's start from the X mass in any case. So you can see that these objects, I mean, I told you that these objects have spin 1/2, but you can even just see it from their commutation relations, especially with the generators of boosts and rotations. And so this is immediately telling you that if you have some fermions in your multiplet, you're also going to have a boson. So the multiplets of this symmetry contain particles with different spin. And the first simple consequence of the algebra that we're going to use is that if you apply twice the fermionic generator, you just get a translation. And the other fact that we're going to use is that they commute with momentum. So since they commute with momentum, they also commute with momentum squared. And so given that the momentum squared is a Casimir of Poincaré, it's also a Casimir of supersymmetry. So in principle, this is already enough to say why supersymmetry can solve the hierarchy problem, because this is telling you that fermions and bosons are in the same multiplet. The mass squared is a Casimir of the algebra, so there are fermions and bosons with the same mass. And since there is a famous symmetry that protects the mass of fermions, which I'm going to remind you in a second, then supersymmetry is extending this protection also to the mass of scalars with spin 0, like the Higgs boson. Okay, I could stop here but I want to be gentle and really do it. Okay, so let's see it, even if it's trivial. I can, for example, compute the mass of some boson in the multiplet, and then I can use the relations that I wrote up there in the following way. So, sorry. Then I can just commute them. Wait, I think I might have inverted it. Doesn't really matter. No, it was okay. So let me use the commutations, and then the fact that they act as a translation. So this is just the same state translated. So by this very simple chain of equalities, we found that there are masses of bosons and fermions in the same multiplet that are the same. The reason why this is interesting is another elementary fact that I probably have seen in quantum field theory courses, which is that there is a symmetry that protects the mass of a fermion in quantum field theory, which is actually what is changing the calculation of classical electrodynamics for the electron. So if you write down a Dirac fermion in terms of its Weyl components, so far I tried to use only Weyl notation. The only time where I switched was when I wrote down the W vertex for the KO mass. I hope that didn't bother you. If you want me to, I can write it in terms of Weyl fermions. So from here, you see immediately that the kinetic terms have two symmetries, and in particular have this one, that the mass breaks. If you want to formally restore it, you can give spurion properties to the mass. So this formally restores the symmetry that people call chiral symmetry. And so now, well, we have just seen that if this symmetry is realized in nature, there's going to be a partner of the Higgs that people call the Higgsino, whose mass should be equal to that of the Higgs boson if the theory is supersymmetric. And so now, when I do my estimate of the Higgs mass that we were doing before, I cannot put on the right-hand side any scale that transforms in the same way as the X mass under dilations. It also has to transform in the same way under this chiral symmetry. And the only object that I have in the theory that transforms like this is the three-level mass of the fermion itself. So even without doing the calculation, I know that the X mass in this theory, if you want, I can put an at here. So the measured X mass in this theory has to be proportional to the three-level one times something that I don't know. Okay. In principle, I could still have some logarithmic sensitivity to a big scale, but not the quadratic one that I had before anymore. Of course, we know that this symmetry is not realized in nature exactly. Otherwise, we would see a doubling of the spectrum of the standard model. For each particle that we see, we would see one with different spin and the same mass, which we don't. So we know that there is some breaking. And so in reality, the X mass is going to be equal to the mass of this X-zeno plus something that breaks supersymmetry. But again, I cannot put any scale here. I can only put a scale that breaks supersymmetry. So if you want now, we have some selection rules also for the breaking of supersymmetry. And whatever appears on the right-hand side of the mass difference between X and X-zeno must break supersymmetry in the right QT. And as we will see in a second, this will both allow a precise statement of the problem and also a solution to it. However, maybe this is a good time to stop because to show you explicitly what I'm saying, I need to introduce a few definitions. So I think there is no point in going through all the definitions and then stopping later. So we can have our break. Yeah, so let me make a correction that Patrick correctly pointed out. So when I put the log here, actually I was meaning to tell you later, but I should have just put it on the second line because this log also can appear when you break SUSY. Otherwise, again, you would have some selection rules problem. Okay, now let's see. Let's see what's a bit more precisely the fate of the X masses in this theory. So the core of the argument is already here. So you see that if you don't break supersymmetry, you're relating the measured X mass to the three-level mass of some fermion, and you have no sensitivity to high scales. So the estimates that we were doing before with mx that has to scale like M-Planck squared or whatever other large scale coupled to it squared do not hold anymore in this theory. So there is no sensitivity to high scales and no problem with accommodating the value of the X mass that we measure. However, as I said, we know from experiment that we have to break supersymmetry. But even if we break supersymmetry, so now what we can say from symmetry on the X mass is the second line, still the problem is not exactly the same as before because our estimate is telling us that at most mx squared is comparable to the SUSY breaking scale squared. And since this SUSY breaking scale squared, by definition, in the SUSY breaking scale transforms non-trivially under supersymmetry, it cannot be just any scale in your theory. It has to be a scale that breaks supersymmetry and obeys certain selection rules. And so it can be anything. So it's natural for it to be much smaller than M-Planck. And in practice, if you believe that this is the theory that extends the standard model, you can make a prediction for the SUSY breaking scale in the same way that we did for these historical examples of the pi of mass difference and the k of mass difference and the electron self-energy. And you would predict that in the best case, this SUSY breaking scale, so if it enters at tree level in the same way that I did here, then you're predicting it to be roughly the X mass. But it's not necessary that all particles feel SUSY breaking in the same way. So it might be that really the Higgs is coupled only at one loop to SUSY breaking, in which case our estimate would be something like this again. And then our prediction for the SUSY breaking scale would be of order TV squared. The reason why I'm putting y top here is that this whole story works if I extend the whole standard model to being supersymmetric. Let's say I forgot about the top sector. If I forgot about the top sector, then my estimate would still be what we had before, with this new scale here being completely unconstrained by SUSY breaking selection rules, because I have a dimensionless coupling that breaks supersymmetry if I don't extend it also to the top sector. And so this estimate would perfectly respect the selection rules of all symmetries. So if I want to explain why the Higgs mass is small, I have to extend supersymmetry to the whole standard model so that these kind of contributions don't exist anymore. And so these simple observations are showing you, as I was saying, on the one hand, that we can potentially solve the problem. But they're also showing you that in this theory, the Higgs mass is calculable, and there is potentially an actual problem. So this is, if you want, the second consideration I should have made. The first one is that MH is calculable, and there is a potential problem. And you can see it even just staring at the simple estimate, because here on this side, we have the Higgsino mass that we can measure independently of MX. We measure the mass of the Fermi. And then we have this SUSY breaking scale that also we can measure independently of MX. We can measure the masses of some other standard model particle that is sensitive to SUSY breaking. And so now, even without doing the calculation, which I'm going to show you in a second, you can conclude that in these theories, even if there is some soft breaking of supersymmetry, the Higgs mass is calculable, and in principle, if the soft breaking of supersymmetry is small enough, you can also explain why it's small. Notice that if I were to break SUSY with a dimensionless coupling, so when I say soft breaking, I mean by a dimensional scale. Let's say I break it with a dimensionless coupling, then I'm back in the standard model, because I can still write these terms in the estimate. Okay? So what I'm going to do next is just to essentially replace these ellipses and these SUSY breaking scales with something a bit more concrete. But essentially, I've already told you the whole point of the story. So, so to actually show you what the Higgs mass looks like in supersymmetry, I have to introduce a few things. The first one is that if you extend the standard model minimally, so just add the minimal particle content consistent with the algebra I wrote down before. In addition, so you need two Higgs doublets. One, for two reasons. One, that the gauge groups of the standard model become anomalous if you don't have the second Higgs doublet. And the second one is that you cannot write Yukawa couplings anymore, because if you remember, last time, in purely within the standard model, we wrote something like this. But, well, again, I'm going well. So, but in SUSY, so if you want to write, the simplest way to write a supersymmetric Lagrangian is to start from a superpotential which is holomorphic. So it only contains fields and not their daggers. And so if you want to write all the Yukawa couplings, and let's say you write this one, now you have a problem, because you cannot write the one for the down quarks or the leptons. And the only way, okay, the simplest way in which you can do it is by adding a second doublet which has hypercharge opposite to the first one. And from here, you also see why I called one H down and one H up, because one is the one that couples to up quarks, and the other one is the one that couples to down quarks and leptons. And okay, nicely enough, this extension also makes the whole theory non-anomalous. So we are happy. So now, when you write down the X potential, you have to write the potential for these two doublets, which looks like this. Always forget the last word. Let me look it up. So those GY and GW are gauge couplings of weak interactions in the standard model. Okay, surprisingly, I remembered everything up to there. So this mu squared and the quartic couplings are supersymmetric. So the mu squared comes from this term in the superpotential. But I've also added SUSY breaking contributions. So these are SUSY breaking, and I've added them because if I didn't, I couldn't get an electroweak symmetry breaking that resembles what we measure in the standard model. So I'm forced to do it.
So,
yes.
In the first line, why do you put modulus squared for MHU squared?
Did I? Maybe I made a mistake. Yeah, I shouldn't have.
Theta can be negative.
Yeah, you're right. You're right. Yes, I just confused myself when I wrote mu squared. Indeed, there's no absolute value. Okay, so from here you can see already what I promised you last time. You can see that there is a problem already at 3 levels. So whenever people tell you that naturalness problems exist only because we don't know how to do loop calculations, they're already telling you something. You should already be suspicious. Because from this Lagrangian, you can look for the minimum of the potential of the two X doublets. So let me say that at the minimum, the two doublets have webs that look like this. Then I can write at 3 level the expression for the weak scale in terms of the Lagrangian parameters that I wrote down there. Where the weak scale is the sum of the squares of the two minima. This is what enters, for example, the W mass or the Z mass, because both these doublets couple to gauge bosons of SU2 and hypercharge through their kinetic terms. So when you expand these kinetic terms around the minimum, you're going to find that the W mass and the Z mass are proportional to this number. So this is the number that, in some sense, fixes the scale of the electroweak sector of the standard model. And so using that Lagrangian, you can compute it, and it's this. Now, this time, the absolute value squared is there. Sorry, the absolute value is there, not squared. So here I turned the simple symmetry estimate into something precise at tree level. And you can already see the potential problem and the potential solution. So here I've written down the weak scale, something that I can measure. Okay? I measure the W mass there. Then I have two gauge couplings. I can also measure them. I measure the muon decay and electron muon scattering. Then I have these SUSY breaking masses. Well, in my theory, I have these 2x doublets. And so in the end, I have 4 propagating degrees of freedom. Let me call them A, H plus or minus, big H, and small h. In total, these 2 doublets are complex doublets, so they have each 4 degrees of freedom. 3 go into the masses of the W and Z, and the remaining ones are these, 5 actually, because H plus or minus is 2. And so here I have 2 SUSY breaking masses, MH up and MH down, and these 2 webs. So let's say I measure the mass of 3 of them, which are not the standard model-like Higgs boson, the other 3. Then I can measure this mass, and one of the webs. Then this electron fixes the other one. So I've measured everything up to here. What I'm left with is this mu. This mu is the supersymmetric mass of the Higgs, so it's also the mass of the fermion. And so I measure the Higgsino mass. And there you go. So I've written down the weak scale, not in terms of the Higgs mass, but its vacuum expectation value, all in terms of measured quantities. And now let me say that I go ahead, do my experiment, and find no trace of supersymmetry at a TV. But I know that supersymmetry exists at some larger scale. Now I do have an actual problem, because let's say I know for sure that I have a theory where the Higgs mass, or the weak scale, if you prefer, are down here, and the SUSY breaking parameters are up here. Now, why do I get this result? I mean, it's weird, because on this side, I have parameters that are much bigger than the one on the left-hand side. And so this is the actual hierarchy problem. So if I have a theory where the Higgs mass can be calculated in terms of observables, and I find that 2 of them, or 3 of them, or n of them are much bigger than the measured Higgs mass, and they have to finally cancel each other to give you the measured value. Maybe the more striking example would be if I found that MH up and mu were both huge and canceled each other, because mu is a supersymmetric parameter and MH up is a SUSY breaking parameter, so a priori they have nothing to do with each other. Notice that if really I found no trace of supersymmetry up to some large scale, I'm really saying that everything is up here, also mu, because it means that I've not found anything, So here I'm really saying that there is a cancellation between parameters that a priori have nothing to do with each other, the supersymmetric mass mu and the SUSY breaking masses, MH up and MH down. And so you can take it both ways. So if you believe that SUSY is absolutely there in your theory of nature, this is telling you that not measuring SUSY yet poses a problem to your theory of nature. So you have to explain why these unrelated parameters cancel each other finally. A natural problem in terms of observables.
Sorry.
Yeah.
Question. I don't understand. You're at 3 level. Why you have V8 is not V3?
Yeah, they are. I mean.
Yeah, you have a V3 on the left and V8 on the right.
No. Well, yes, these are the same. These are the same. Yes. I mean, I wrote 3 just to emphasize that
okay, they're the same.
But yes, they're the same.
I mean, does your argument work? if you don't know what V3 is on the right on the left.
Yes, I wrote it like this just because it was easier, but I could have written it. I wrote it like this, not to introduce too much notation. In reality, people call this, if I remember correctly, tan beta. But anyway, it's an angle in the X sector that you can measure independent. So this one, you can imagine, let's say I measure it from the W mass. This one, you can measure it, for example, from a vertex that looks like this. So you can get this term from some other independent measurement. So this combination of the up, down over V3. And this is just one example. There are actually multiple measurements in the X sector that can give you this combination. Even the coupling of these new X's to the fermions are sensitive to this angle. In particular, say the couplings of the charged X to a down and a up quark, they really depend on this angle beta, so on the ratio between these terms. Thanks, actually, that was perfectly timed to make it clearer. Well, in practice, I've already told you all the important things about supersymmetry that there are to say, but to show you that I'm being really completely honest, I can also do the same at one loop. So at one loop, as in the standard model, the dominant contribution to the X mass is going to come from the top sector. It's the largest coupling to the X, also in this case. And so you can add the Lagrangian, the supersymmetric partners of the top quark. And they're going to have a coupling like this. And then they're also going to have some SUSY breaking coupling like this. And now I'm going to make the notation clearer in a second. So the top quark in the standard model has two vowel components, so a total of 4 degrees of freedom. So I have to add 2 complex scalars to complete the supersymmetric multiplet. This Q tilde is a complex scalar, which you can think of as the partner of the SU2 doublet that contains the top quark. So it also contains a partner of the bottom quark. And this TC tilde is a complex scalar, which is the partner of the right-handed top quark in the standard model. From this Lagrangian plus the usual standard model Lagrangian, you can also compute loop corrections to the weak scale, which are most easily phrased as loop corrections to this parameter. So you can correct MH up very easily and then plug it back here in the 3-level contribution. And if you do so, you're going to find the following. So this is some SUSY breaking scale that I'm conventionally normalizing to a TV. And so, well, you see that at one loop, essentially, you're finding the exact same thing that you're finding at 3 level. So if these masses are much, much bigger than the naive expectation from cutting off the loop at a TV, then you have to explain why they cancel each other and give you a small value for the weak scale. And again, also in this case, here it's even more manifest. You can measure all these parameters independently of the X class. So you measure, the stop mass eigenstates and their mixing, and you measure these three parameters. You measure some top quark properties, and you measure the top Yukawa, and then you measure, I don't know, some Slepton mass, and you measure the SUSY breaking scale over here. So going to one loop, I mean, I went to one loop just for completeness, but the important takeaway point from this lecture is that the hierarchy problem exists at tree level, and it exists cleanly in the theories where you can compute the X class. What else? We still have a little bit of time. In which case, well, let's say I will add one more detail about supersymmetry, which is not crucial, but might dispel some confusion if you encounter different expressions for the weak scale in supersymmetry. And also, it kind of ties nicely to the question that Stefan asked last time, to which I didn't reply very nicely on record. So the core of what I wanted to say about supersymmetry is already behind us. But if you browse the literature, you will find expressions for the X mass in supersymmetry that are quite different from what I showed you. In particular, you will find the following. And also at one loop, you're going to find like this. And I'm going to define everything that I haven't yet defined in a second. Again, these are the dominant contributions coming from the top four. So this MA is what we were saying before. So in the X sector, there is another X boson that has mass MA. And well, I defined this MS is not what it was before. This is the mass of the two partners of the top, so the two stop quarks. Sorry, without a square. And Q1 is some sort of intermediate scale between the top and this one. And Q2 is this scale. And finally, XT is the parameter in the top Lagrangian that I introduced before that breaks supersymmetry times some SUSY preserving contribution. Now, why did I bother to write this down? Well, the reason is very simple. Try to take the limit of MA going to infinity by I here. What you're going to get is MZ. Same here. Try to take the stop masses to infinity here. Nothing bad happens. So it looks like there is no more tuning. In the exact same way as, if you recall the calculation from last time, when we wrote MW, that complicated function of measured parameters. So also in this case, there was nothing going wrong if you took some scale coupled to the X mass and moved it to infinity. The reason why, when you write the X mass like this or the W mass like this, it looks like the tension has evaporated, even if you take mass parameters to infinity, is just that in these expressions you've already tuned. So by fixing mz, you've already fixed in the standard model the unknown parameter in the measurement of the X mass. Okay, so by expressing everything in terms of mz, essentially you are saying in the standard model that you've already measured this unknown parameter with the X mass. Instead, in the supersymmetric standard model, by fixing mz, you're saying that you've already accepted the tuning in the weak scale that we were seeing before. That's it. Okay, it's just that you're hiding the tuning in the measurement of mz. It's not that there is no more fine tuning anymore. This was some sort of detail, but if any of you is more interested into this kind of ideas, you will encounter this expression and you might wonder. Okay, so we have seen that if you were to measure supersymmetric partners around a TV, let's say, or lower in the case of, for example, if you remember the formulas that I just deleted, I'm not sure why, that mu parameter was entering at P-level in the weak scale. So you want it to be comparable to the weak scale itself, which means that if you want everything to be natural, you expect xenos at 100 GeV, 200 GeV. Instead, the stop masses were entering at loop level with white top in front, so you expect them to be at a TV. And as you know, we have not seen any of that. For now, I'm not going to comment on this fact, but what we learned today is that the hierarchy problem essentially is telling you that the standard model should be extended non-trivially. The simplest way in which you can extend it and not have a problem is supersymmetry. But experiment was not so kind to us. I mean, everyone was excited to turn on the LHC and left before that, precisely because of this estimate of the one I was showing you before. So people were excited to turn on LEP. At least some people were excited to turn on LEP because of this term, the one that enters at P-level and is supposed to be a few hundred GeV. We didn't see it. Okay, I mean, still there was room for an xeno around 200 GeV. Okay, it's very hard to see an xeno at the LHC, and there is still room for an xeno around 200 GeV. And so, but then people were excited to turn. So LEP didn't exactly kill the idea, because if you just look at this estimate, you might say, okay, we've explored up to 100 GeV. Where are the partners of the leptons or the X? But if you go more into the details, you'll see that there is no tension between experiment and this estimate. And so people now were excited to turn on the LHC because of this term. Because now, sure, the stops can be much heavier. They can go up to a TV because here there is a log. But they're also strongly coupled. So we're going to see plenty of them coupled to gluons. We didn't yet. We haven't yet. So for now, I'm going to leave it at that. Because I want to try to present to you an alternative to supersymmetry along the same lines, so still along the lines of symmetry. But then next time, we're going to see how the symmetry-based idea compared to experiment. We're going to do it very quickly. I'm going to devote order 50 minutes to it just to show you a compilation of experimental results and why they're in tension with this idea that the right extension of the standard model might be these ones that explain the mass based on asymmetry. As a spoiler, well, the bottom line is that the longer we wait, the worse these ideas look, but they still look much better than everything else we got, as you will see as we get to the end of these lectures, when we essentially started conservative with the cleanest explanations for the X mass, and then we're going to go progressively crazier towards the end. So supersymmetry was by far the easiest possible explanation. Now, let me talk about another one, scale invariance. So for some reason, people don't like to present the core of this idea in the cleanest possible terms. So you will find a lot of ideas that are called composite X or warped extra dimensions or whatever. And no one is going to straight up come to you and tell you it's just scale invariance, just because they know. I mean, okay, they just expect you to know as well. But pedagogically, I want to present it backwards. So I'm going to start with simple symmetry considerations and then show you a glimpse of the models. Of course, historically, it went the other way. People that were fully aware of what scale invariance is built explicit models that include the standard model and protect the X mass, and never cared to mention that scale invariance is what protecting the mass. Okay, so why is scale invariance useful for us? Because as we've seen in the last lecture, the X mass, if you treat it as a spurion, transforms non-trivially. So if you rescale all space-time coordinates, the operator associated to the X mass breaks scale invariance, and also the cosmological constant breaks it. And if you want to restore it, you can give them these spurionic transformation properties. And so you immediately see that you have a potential analogy with supersymmetry. If you can build a theory that incorporates the standard model and it's scale invariant above a certain scale, so let's say you have, again, the standard model down here, up here you have scale invariance breaking, then your new estimate for the X mass is going to be something like this and not M Planck anymore. And we've seen at the beginning of the lecture an example of how scale invariance can generate a big hierarchy naturally. Because a theory that respects this symmetry essentially contains only marginal operators of dimension 4. So if you remember the little exercise we had before, your low scale, which in this case is the scale where scale invariance is broken, can be an order 1 number to a very large power if these operators are just weakly relevant. And so there is a natural way to explain why there is a big hierarchy of scale in a scale invariant theory. The name also kind of suggests it. And now, well, we are left with the problem of explaining why, in the same way as supersymmetry, why we don't see an approximately scale invariant standard model, because there are all sorts of couplings that break this symmetry. We've seen it last time. So when we were doing our dimensional analysis estimate for the X, we were seeing all these masses breaking scale invariance and having some spurion transformation properties under it. So let me tell you how, well, let me actually first start from here. Okay, let me give you an explicit example of how a hierarchy can be generated by an operator that is almost marginal but not quite. And the example is QCD, as I was telling you before. So if you write down the action of QCD, at the classical level, it's scale invariant. If, let me for now forget about quark masses. So this G mu nu, as usual, is the field strength of the gluons. This A goes from 1 to 8 are the generators of SU3. This is a covariant derivative which includes the interactions between the gauge bosons in these Gs and the quarks. And again, if you do the exercise that we did last time of deducing the scaling dimensions of the fields from the kinetic terms, and then asking how these operators transform under a scale transformation, you will find that this action is invariant. At the quantum level, the gauge coupling breaks this scale invariance. So these operators are going to get a dimension that is 4 plus some correction proportional to the coupling. But as you know, this coupling runs to smaller and smaller values as you go to high energies. So, say, start again from the weak scale and go up to some large UV scale. If you think that the running stays the same up to there, you will find that alpha strong at the high scale is much, much smaller than 1. So it's possible that QCD at this scale is completed into something that is scale invariant also at the quantum level, not only at the classical level. So maybe it really flows to a fixed point where the gauge coupling is 0. If you imagine that this is the case, well, then you can compute what scale you expect for the coupling for lambda QCD that we were mentioning before from these very same arguments. So in this case, you can do it, for example, from the running of the coupling. So conventionally, one calls lambda QCD the scale where this coupling becomes order 1. And between lambda UV and lambda QCD, the coupling is running only logarithmically. The reason is that there are only operators which are marginal modulo small correction. So when you compute, for example, these kind of things, the scale here is always going to be raised to a small power. And if you take epsilon to 0, you will precisely find a log. Okay. A more precise way of seeing it is if you compute the running of the coupling, then you're going to find, let me just get the order 1 numbers right, then you're going to find the log of the ratio of these two scales is the following number, where I'm calling lambda QCD the scale where the coupling becomes equal to 1. So, okay, so this is a simple way to generate a big hierarchy of scales. We have some gauge theory that is approximately scale invariant, even if scale invariant just at the classical level. Then the gauge coupling itself is going to generate perturbations that deviate from exact marginality by a small amount, where this epsilon is of order of a loop factor. And then the slow running coming from these almost marginal deformations, but not quite marginal, generates a new scale lower than your fundamental scale, but that can be exponentially separated in principle. So you see if you exponentiate both sides of this equation. So this is a simple way to write down an actual theory that does what we said in terms of symmetry, or in this more abstract language of operators. You might worry that in actual QCD this is not the case because there is one relevant deformation, which are the quark masses. So if you are really honest, you should also add something like this. And here, actually, yes, I forgot one bifermion. However, well, we've seen that quark masses respect this chiral symmetry, and it turns out that the selection rules of this chiral symmetry enforce that they run in the same way as a marginal operator. So since you can only write on the right-hand side something that transforms under chiral symmetry in the same way as the quark mass itself, in the running, the only dimensionful parameter that can multiply everything is the quark mass itself. And so in the end, the large scale can enter only logarithmically also in the quark mass. So even if we have this operator that naively, if you just do a dilation, transforms like a relevant operator, is its dimension 3, its running, it's the same as that of a marginal operator because of the selection rules of this chiral symmetry. So in practice, also, if you add quark masses to QCD, you're still not surprised that lambda QCD is much smaller than M Planck. Okay? And, well, you could take this lesson from QCD as an indication of what happens also for the X mass. So maybe it's exactly the same for the X mass, that at some scale, the whole standard model is recompleted into something that looks like a gauge theory that's approximately scale invariant, and then the big hierarchy is stabilized in this way. However, well, we immediately have a problem that you don't see a bunch of strongly interacting states right on top of the X mass. Actually, we already measured up to a factor of 10 or more above the X mass at the LHC, and we found no trace of the scale where the standard model should become strongly coupled, change completely, be described in terms of new degrees of freedom. And that's what killed Technicolor. So what people call Technicolor theories are these essentially. So you imagine that the standard model is recompleted into gauge theory, which is described in terms of a new gauge group that includes a subsector of its global symmetry, also the standard model gauge groups, as some new fermions that condense at the weak scale and give you the X, the Ws, etc., etc. But, well, we haven't found it. However, this is not the end of these theories based on scale invariance. And again, I mean, QCD comes in handy because maybe the Higgs boson is not a generic bound state of this new strongly interacting sector, but maybe it's a Goldstone boson, which could create a separation between the scale where you should see the whole new strongly interacting sector and the standard model itself. So in QCD, as we were saying before, at around the scale where the coupling becomes strong, you see something like the rho meson. So you're closer to a GeV. And then somewhere below, at around 100 MeV, you see pions. And these pions are Goldstone bosons of a global symmetry that's not linearly realized in QCD. And maybe it would be the same for the Higgs boson in these theories. And this is what people call composite Higgs. And I'm going to give you possibly the simplest example of this. So you have to imagine that at the scale of the breaking of scale invariance, there is some sort of new strongly interacting gauge group with some global symmetry G. Okay, so there is some G gauge, and this new sector has some global symmetry G. And this symmetry should contain at least the electroweak sector of the standard model. It could contain also the strong sector, but for our purposes, it's sufficient that it contains the electroweak sector. And as far as I'm aware, the simplest possibility that has been proposed is that G is SO5. A subgroup of SO5 is SO4, which is locally isomorphic to SU2 cross SU2, and you can identify this one of the two SU2s with standard model weak interactions, so you're going to gauge it. And you're going to identify the diagonal generator of the other SU2, that conventionally I'm going to call it right to distinguish it from the left-handed one of the standard model. And this I'm going to call hypercharge. So we see already from not even having written the theory yet that gauging this group is breaking the original symmetry of the strong interactions. And so the Higgs boson is not going to be an exact Goldstone boson. Some potential is going to be generated by this gauging because I'm gauging only a part of the symmetry group. So let's take this theory just for illustrative purposes, just because it's the simplest one. What we're going to imagine is that say at the scale where the strong dynamics starts to become strong, you have some linear sigma model that looks like this. With phi in the fundamental of SO5. And this is possibly the simplest way in which you can describe some Goldstone bosons of a non-linearly realized SO5 with a linearly realized SO4. Okay, you can see from the way I've chosen the potential that if I'm starting with an SO5 symmetry, then only an SO4 subgroup will be linearly realized. I'm going to show you more explicit in a second. And then I'm going to have some Goldstone bosons living in the coset SO5 over SO4. More physically, you can forget about this group theory and just notice that I've written a potential with a flat direction. So whenever phi obeys this constraint equation, the potential remains the same. And so I'm going to have some part of the degrees of freedom of phi that have no potential and no mass, namely something that looks like the phase of phi. And well, as you might know, if you don't and if you want, next time I can give you a quick review. There is a general way of parameterizing the massless field of the massless fields in this case. And for our choices of groups and fields, this general way of parameterizing the massless fields translates into this. These X here are the generators of SO5 that are in the coset. And these phi here are the massless fields. So if you plug these back into the original Lagrangian, you will find that these phi's have no potential. And this sigma instead gets a mass for the G star times F. This is interesting for us because now we have these 4 degrees of freedom that transform in the fundamental representation of SO4. This is something that you can verify explicitly from this expression. And it turns out that in the standard model, the Higgs boson has exactly 4 components. And if you write them in this way, they also transform in a 4 set of SO4. Actually, they transform as a 4 of the same SO4 because we've chosen to identify its isomorphic SU2 left times SU to right, this one with the standard model weak interactions, and the diagonal generator of this one with hypercharge. So these pies are precisely the degrees of freedom of what we would call a standard model like X doublet. And so we have realized a sector where we have a global symmetry, which is Norwegian realized, and the resulting Goldstone bosons are exactly 4 and exactly the degrees of freedom we need to describe the X. So this seems a very nice model where at low energy we really predict only the Higgs boson, plus possibly the other standard model fields that we have somehow to include into this picture. But for now, let's just focus on the Higgs boson. So there are no extra scalars that can bother us. And so this is an explicit construction that might explain why we see a small Higgs mass, and we also do not see a plethora of new strongly interacting degrees of freedom right on top of it. So you might be happy and think that we are done. Okay, maybe it was not SUSY, but certainly we're gonna go a loop factor above and see all this composite sector. Sadly, it's not so simple, because now actually do plug this back into the Lagrangian and write it in terms of the X. What you're gonna get after you integrate out sigma, which is heavy, so let's say it lives roughly at this scale. It lives at this scale because if you remember the story with QCD, we introduced this F pi. This F is exactly the equivalent of F pi, so it has dimensions of a web. The mass of sigma is this gauge coupling G star, which is the coupling of the strong interacting gauge group times the web. So it's precisely what we call lambda QCD for QCD. Anyway, so but now we are below lambda QCD. We're at the scale of the pilots. We might think that we are done and we're safe from experiment. But even if you found a way to take the scale much larger than a loop factor above, which I have no idea how to do, but let's even say that you could, you would still have the following problem, that if you plug back, as I was saying, the pions into the Lagrangian, then you're going to find the following. Avoid mistakes. So at the scale f, the Higgs looks horribly nonlinear, so not at all like the simple Lagrangian we wrote in the standard model. If you were to canonically normalize the kinetic term, all the Higgs couplings would change at order 1 compared to this prediction of the standard model. You will get these factors of h squared over f squared all over the place. That is going to change the predictions of Higgs coupling to standard model particles compared to what we measured. So even if we could decouple completely the scale where actual scale invariance appears, we would still have the issue of not seeing, of not seeing a compact object, essentially. Goldstone bosons are phases. They're defined modulo 2 pi. The Higgs doesn't look at all like a phase of the LHC, unfortunately. And you can see this even before actually doing the exercise, because at this level, you see, I didn't even write a potential for the Higgs. This is only corrections to operators with derivatives of the Higgs boson. If I wanted to compute a potential, I would have to compute what's coming from the breaking of this SO5 from gauging. I would have to decide how to include the top into the strongly interacting sector, which possibly is going to generate another contribution to its potential. And finally, well, I'm not going to do it explicitly, but I would find something like this. I would find where these A's are coming from all the different sources of breaking of SO5, and these B's similarly. But the only dimension full scale in the problem is F. However, so if I imagine that this thing naturally sums to some order 1 number, you see all the nonlinearities in H at order 1. So you predict that the X-Web is of order F. And then once you canonically normalize this kinetic term, you find all sorts of deviations from the standard model predictions at order 1. And so for these theories to be compatible with experiment, you still need some amount of accident. So you need to tune these order 1 numbers in such a way that the X-Web is something different from F, and that V squared over F squared is order 1%. So this would give you agreement with measured X statics. So I think that today we can conclude it here. So there are two wonderful symmetries that could explain why the X mass is what we see. They both predict new states compared to the standard model. If you decouple these states, you find accidental cancellations between our related parameters to explain the X mass. If you don't decouple these states, you expect signatures at LEP and the LHC that we have not seen. So I'm leaving you on another cliffhanger, and next time we're gonna give a few more examples of ideas based on symmetry. For example, a realization of this scale invariance paradigm in 5D in an ADS space. Then summarize these tensions that today I've only alluded to a bit more precisely, but no more than 10 minutes. And then we're going to try to draw some conclusions on these ideas based on symmetry, and then move on to completely different ideas that can explain the observed value of the X mass. Thanks for listening, and I'm happy to take any questions.
Yeah. When you were talking about kind of the Suzy model in particular, you sort of highlighted that the issue was fine-tuning, which is sort of the classic way of presenting it. You've got a bunch of parameters, there's no reason they should connect. Last time you mentioned that, okay, one objection someone can have is maybe the parameters just are what they are, they're fine-tuned, who cares? And you kind of said there might be some deeper quantum gravity reason why that's not allowed. I'm curious if you're going to get into that in more detail later.
Sorry, the question is whether quantum gravity could arrange these parameters in such a way that there is no tuning,
or vice versa, rather than there's a quantum gravity reason why tuning is bad. Basically, you know, you can say, okay, tuning is bad because these things have no reason to do with each other, but that's kind of fuzzy. But is there a deeper reason tuning is bad?
Okay, well, so as far as I know, we're not aware of any deep reason why tuning is bad. So it's entirely possible. So I didn't dare to write it in the list of possible explanations, but a possible explanation for both the CC and the X is that they're just tuned. End of the story. Another possible answer to your question is that we don't really know what are the fundamental parameters of the theory at high energy. So when I show you this supersymmetry calculation and I tell you that these parameters have to tune and cancel each other, I'm in some sense making an implicit, I'm making an implicit assumption that I haven't told you because I wanted to tell you next time when we talk about the multiverse, which is that those are the fundamental parameters of the theory. Because if those are the fundamental, so let's say, imagine that what's defined in the UV is the Suzy breaking scale. Then you can deduce a probability distribution for these parameters in the multiverse, if there is a multiverse, which is the only way in which you can make statistical statements about this issue. And then you will find that these parameters are either uniformly distributed or power law distributed around some value. And then you actually see that it's very unlikely that they cancel each other. But this is an assumption. So it's assuming that what the UV theory cares about is the SUSY breaking scale. That's the fundamental parameter. But to be honest, we don't really know. Okay, maybe the quantum gravity theory really cares about the Higgs mass, or more likely, the cosmological constant. And it doesn't care about what we think are the fundamental parameter and enter the calculation. So what looks like a tuning from this perspective might just look from a more correct UV perspective, like the fact that these parameters have some significance and they must have some values, otherwise the theory is inconsistent. And so all other parameters arrange themselves in such a way that we see this weirdness of low energy. So the answer is that there is no answer. And the reason why I like the question is precisely because it forces you to think about high energies in these terms. So it's a purely low energy observation that forces you to ask these questions. How the hell does the UV theory look like? What are the fundamental parameters? And it's not trivial to find low energy handles that get so deep into high energies. Any other questions? Yeah. How they fit into this picture? Well, they essentially, I mean, you could say that here I have some grand unified. So if you run the standard model catholics in the standard model or in the MSSM, they tend to unify around between 10 to the 15, 10 to the 16 GeV. The standard model don't unify very well. In the MSSM, they unify better. In these theories where you unify all the gauge groups of the standard model in a single group, you typically expect proton decay from new states in the theory. And the experimental bounds are around 10 to the 16 GeV on the scale where you can generate an operator that induces proton decay. So if these GAN unifying theories exist in nature, presumably they exist at this scale. And so you can essentially replace and planking what I said with the GAN unified scale if you want to fit them in the picture perturbatively. I mean, maybe GAN unification perturbatively and below the scale of quantum gravity. It's not impossible the GAN unification happens above in some way, and we don't know. But yeah, if you want, let's say, a simple, clean, bottom-up picture where you don't need to worry about quantum gravity, you can do what I said, like replace and plank with NGAT. You're going to have a few orders of magnitude less of a problem, but still.
More questions? Online, maybe. Do you have questions? Okay, so if not, thank you again.